Good morning, everyone. I'm Ria Chaudhary from the Catalyst Group, and we're delighted to have you join us today. We also have several other members of the TCG team on the call with us, including our CEO, Clyde Payne, Vice President Alisa Davis, and other members of our team. A warm welcome to everybody. We're very glad to have you with us this morning. Before we begin, just a few housekeeping notes. Please remain on mute unless you're speaking. You'll see a few poll questions during the session. We encourage you to share responses as we go. Your responses are completely confidential and will not be visible to other attendees. Feel free to submit questions in the chat at any time. We'll address them during the live question answer round towards the end of the discussion. And lastly, since we have representatives from competing organizations on the line, please keep our antitrust guidelines in mind. Let's keep the conversation focused on technology, research, and shared industry insights, and avoid confidential or commercially sensitive topics such as pricing, production, or customer-specific details. For those who may be new to TCG, Jorge, do you mind sharing the screen? Thank you.
Yes. Do you see this?
Thank you. Yeah, next slide is perfect. Next slide. Thank you. For those who may be new to TCG, the Catalyst Group is a global consulting organization with over 40 years of experience supporting the refining, chemical, plastics, pharmaceutical, and environmental sectors. We bridge technical depth and business strategy between two core divisions. We have TCG Consulting and TCG Research, which manages industry-focused programs and multi-client research. Through our dialogue group network of global experts, we bring together science, strategy, and market insight to help organizations stay more informed and make forward-looking decisions. Next slide, please. Our key member-driven initiatives are the Industrial Energy Transition and Decarbonization Consortium and the Catalyst Advances Program. Through IATD, we track emerging technologies, benchmark practices, deliver actionable insights across the energy and industry value chain, helping companies stay ahead and informed of rapid technological change. Through CAP, we focus on emerging catalyst technologies, benchmarking innovation, and scale-up pathways while providing technical and market insights across sectors. Together, these programs bring industry leaders and experts together to share learnings, identify development gaps, and stay ahead of evolving trends. And today is just one of the many examples of how we bring that collaboration to life. Now turning to today's topic. Next slide, please. AI-driven advances in AI catalysis, AI in catalyst and process design. Artificial intelligence is rapidly reshaping the way catalysts are discovered, materials are optimized, and processes are designed, accelerating R&D timelines and enabling more data-driven innovation. AI, machine learning, high-throughput experimentation, and advanced simulation tools are moving from research concepts into practical workflows and across both industry and academia. Today's session brings perspectives from SwissCAT Plus, Oak Ridge National Laboratory, and SandboxAQ to discuss how these AI-enabled approaches are being applied in real research environments, what challenges remain, and what breakthroughs lie ahead. We're pleased to be joined by an outstanding panel of experts, Dr. Stefan Leichenauer, Vice President of Engineering at SandboxAQ. We have Dr. Paco Laville, Managing Director of SwissCAT Plus, and Dr. Brian Etz, Research Scientist at the Oak Ridge National Laboratory. Moderating today's session is Jorge Benavides, Innovation Lead at Ital Biotech and Vela. This session will follow a panel-style question-answer driven format, and we'll conclude with a live question-answer round at the end. With that, let's get started. Jorge, I'll hand it over to you to kick off the panel discussion.
Yeah, thank you. Thank you very much, Ria. I'll start with a short introduction on the combination of artificial intelligence and catalysis. This was done in the context of a bibliographic review I did in the RealCAT, a high-throughput facility in Lille, France, along with Dr. Frank Duminil. So artificial intelligence are algorithms where you get inputs and you obtain human-like behaviors. It's rational, but without necessarily using logic rules like it's done in programming. And we can have narrow AI, which have specific inputs, outputs, and broad AI, which is the one that can solve any task within a context. It's theoretically limited by math and creativity, but actually, and as we have seen with the advent of AI, practically limited by data availability, human knowledge, and also energy. And here in this slide, we'll see why it is so challenging, but at the same time so interesting to apply to catalyst design. Catalyst design, it's a field that has a lot of different interacting phenomena at different scales with different time frames. For example, we have atomic scale, we have nanometric, millimeter, then morphology of a catalyst, we have reactor scales, we have femtoseconds, nanoseconds, we have second residence times, we have days for deactivation, and we also have a lot of physical chemistry phenomena interacting, transport phenomena, reactions, phase distributions, etc. It's complex, it has almost infinite variations, but there is so much potential yet to explore. What we did at Lille is that we identified 3 different layers where AI and catalyst design could be applied and mixed together. And these layers work like in a Russian doll, one that is inside the other one. The first layer of potential for applications and the applications that we saw is characterization of a single experiment, which in which the inputs are typical spectra, infrared Raman, etc., microscopy, for example, and the artificial intelligence interprets a single experimental instance. And we saw that there is a strong progress in this field with specific analysis techniques, but it is limited by noisy heterogeneous data. Also, multivariable integration is still immature, but there is so much potential to integrate these characterization techniques with kinetics and real-time insights. The second layer is optimization, which for which the input for the AI is not a single experiment, but is a whole set of experimental data, different conditions, performance, catalyst synthesis conditions, etc. And the artificial intelligence then graphs this set, its results, and suggests a possible next batch, either for exploration or for further optimization. And we saw here that there are a lot of cases where there have been closed loop Bayesian optimization systems that already outperform the manual optimization that is done in high throughput facilities. However, it is hard to generalize. It is hard to take algorithms that work within a reaction family and transfer that to other reaction families, for example. But this is the kind of advancements that are needed in integration with robotics in order to drastically reduce actual development cycles. Then the third layer is no longer a single experiment nor a batch of experiments, is the whole space of exploration, which is here the potential for discovery. And we saw here applications that have theoretical or computational data, for example, from density functional field or atomic or molecular information. And the AI tries to suggest a catalyst that may not have been previously studied. And we saw here that there are people building generative models along with density functional theory to scan large chemical spaces However, the novelty that has been found in these applications is still limited. However, there is the potential here to create a high throughput experimentation geared towards discovery. And lastly, we'll switch to today's topic. We have cured several questions for our panel of experts. We currently have representatives from the commercial field, which is Stefan, from scientific innovation, which is Paco, and also national research, which is Brian. And I would like to start with the first question to each one of the participants, which is how does each one of these sectors, commercial, scientific, and national research, view its role, and what do you see as the biggest opportunity in the domain of artificial intelligence and catalysis design? So first, perhaps we can start with Stefan.
Thank you so much, and thank you for having me on this panel. This is a very exciting topic, and I think the pattern that we're seeing with AI as applied to catalyst R&D, it mirrors what we're seeing in a lot of other areas, right? I think one to look at in particular is drug discovery, for instance, which is another area that interests us at SandboxAQ. And there we've seen a similar pattern, and as I'm sure many of you know, for example, there was the Nobel Prize winning AlphaFold model, whose the reason why it was so exciting is because of the amount of scale it was able to give to theoretical analyses of the protein space in that case. And so if I'm going to look at the sort of onion of application areas, the thing that's most interesting for me, and I think most interesting from a commercial deployment point of view, is in that discovery category, right? And exactly the process, right? The process that we imagine, the process that we work on, the process that is interesting for us as we're trying to find new solutions to old problems for the world and for our customers, is around, what can we do that maybe hasn't been done before? And AI-powered catalyst R&D provides like a very clear opportunity, right? And it sort of takes place in two steps, right? One is generate lots of data, and this is before you even get to the AI piece, right? Because AI is fueled by data. And in the case of the discovery layer, that data, as you mentioned, is things like density functional theory calculations, for instance, so that we can teach the AI what a broad spectrum of the chemical space looks like. But of course, we're never going to be able to just calculate all of chemical space, but we do as many calculations as we can. It's sort of like mining a precious metal, right? You invest a lot of GPU hours, hundreds of thousands of GPU hours into exploring some domain of chemical space, and then you train an AI model to that's intelligent enough or architected well enough to be able to extrapolate beyond that, and then that lets you scale up what you scale up your discovery process, scale up your exploration, scale up this sort of virtual high throughput screening process you're able to do. And that's the opportunity for new value creation that brings is something that we haven't seen before, and I think is the most interesting opportunity.
All right, thank you. Certainly a lot of possibilities in discovery. Then I'll ask the same question to Paco from the SwissCAT.
Thank you, and hello everyone, and thanks for inviting me and for organizing the event. So just please allow me to give a bit of background just before answering the question. So SwissCAT Plus is an academic technology platform offering AI-guided, automated, and high-throughput experimentation services to both academia and industry. And our main usage of AI currently is experimentally guided machine learning Bayesian optimization. And for those who are not familiar with those tools, it's basically an augmented design of experiment framework, allowing to explore large parameter space efficiently and rationally. And so basically the model suggests experimental conditions and the output of the experiments train the model on the fly. And now to answer your question related to the opportunities of applying AI in catalyst R&D. So the first one would be the scientific opportunity. I think it goes to what Stefan just mentioned. Working with the latest AI tools and the latest lab automation hardware really allow us to identify new catalyst formulation and process parameters and potentially make discovery much faster than when using conventional tools. So as a scientist, it's really exciting to work at the forefront of this multidisciplinary field of chemistry. And the second opportunity I would like to highlight is more strategic because it's still an emerging field of chemistry, at least. We see a strong interest from both academia and industry to evaluate and invest in those technologies. So most of the time, it's usually easier to secure grants and fund projects those days when you combine the keywords AI and automated labs. So yes, so I see those two big opportunities, scientific and strategic.
All right, thank you very much, Paco. And then I'll ask the same question to Brian from Oakland Research.
Yeah, thank you, and thanks again for having me, and thanks everyone for attending this panel today. So I come from Oak Ridge National Lab, and so my perspective will kind of be tailored to the DOE National Lab ecosystem, which has roughly 17 labs nationwide. But I see our role in this area as kind of threefold. We have the kind of fundamental science and research aspect where we are, Oak Ridge is made up of roughly 7,000 staff of varying disciplines across the domains. And so we have a large knowledge base of expertise that allows us to lead in some of these fundamental research areas that maybe aren't prioritized in other sectors that kind of make maybe the national labs unique. The second aspect I'll highlight is our world-class scientific infrastructure. So we at Oak Ridge operate several of the leading user facilities, both experimental and computing. So I work at the Oak Ridge Leadership Computing Facility, which houses Frontier, which was the first exascale supercomputer. Recently was passed, but we are actually working towards the next computer, which conveniently is called Discovery. But that is another pillar that I would say the DOE National Labs fit into this role of providing world-class scientific infrastructure for the user community, the scientific community. The third pillar I'll highlight is maybe translational impact. So we're able to take fundamental research and some discoveries all the way through the kind of developmental pipeline to partner with industry to help commercialize and deploy technologies to provide some economic benefit for the nation. So we see ourselves kind of bridging that gap all the way from early stage research to final commercialization and helping that pipeline. So with that respect, I think there's many great opportunities for us in this area. But I think the thing I would like to highlight is our ability to leverage the world-class experimental and computing facilities to integrate those across the DOE ecosystem to provide autonomous scientific labs for accelerated discovery and to kind of promote this AI-driven scientific future.
All right, thank you very much for your answers. Now I'll stop sharing. And we will go to the curated questions that we have for each one of our experts. So the first question is for Stefan. The idea of advanced models is to blur the boundary between the computational predictions and the information that actually goes out of the experiments, meaning as we advance, the models become more and more accurate in predicting what is happening in real life. So I would like to know from your point of view, what is the current relationship between computationally derived data and real physical experiments, and how do you see that will change in the future?
Yeah, it's a great question and a very interesting topic. From my point of view, from our point of view at Sandbox, we're solidly on the computational side, right? This is our mission in life, is to take as much of the workflows and especially this discovery process as we can, and push it to the computational side. Like, do as much on the computer as you can should be the mantra that we all have in mind. And there's a very simple reason for that. It's because it's fast and it's cheap and it's so on, compared to physical experiment. Of course, at the end of the day, physical experiment is what counts. You need a thing that actually works. You have to, make the thing. And I and my customers, like, we don't actually care about, say, the catalyst. We care about the end product of the reactions that we're catalyzing, right? That's the thing that really matters, and that's like a physical world kind of process. But the fact is that what we're seeing now, right? Beyond, there's two things that matter, right? There's two things that matter when it comes to making progress. One is scale, and the other is accuracy. And accuracy, the ultimate accuracy, of course, you get from doing a very careful real physical experiment, but you can get that now computationally, and traditionally you could get that through, tried and true tools like DFT and so on. But now you can get near DFT accuracy across a large swath of chemical space at orders of magnitude increased speed, right? Not just 10 times or 100 times, but 10,000 times faster throughput with that same level of accuracy. And once you have that kind of opportunity in your hands, the balance shifts between, okay, this is a thing that now I can do a funnel type approach to my discovery process, where I'm doing a lot of computation upfront, where I'm using these very fast computational models that have good accuracy, and then search, test, do as much as possible with the computer, and then verify with the physical experiment. So the physical experiment becomes the thing that you do at the end when you want to just confirm what the computer is teaching you. But the balance is certainly shifting toward computational heavy.
All right, thank you very much. And definitely machine learning is an enabler since DFT usually uses so much computational power that in the past we were very limited by the computational power. Now the next question is for Paco. As you mentioned, it's becoming increasingly attractive, but also there is pressure, for example, from the European Union to accelerate catalyst discovery cycles. It also happens in America. There is pressure to outpace the traditional research and development workflows. And we would like to know if, from your laboratory, if you could share a concrete example of how AI is being used to support the catalyst design and also improve experimental decision making.
Yeah, sure. So, usually we have several AI-guided projects running in parallel in the labs, covering different types of catalyst classes, so metal-supported catalysts, mixed oxides, high-entropy oxides, and a broad range of applications, CO2 hydrogenation, Fischer-Tropsch, biofeedstock conversion, just to name a few. But maybe one specific example that could resonate more with the audience today is our a recent collaboration we had with a company called Daphne Technology. So Daphne, they are developing a plasma catalytic process to remove methane from industrial exhaust sources. And our role at SwissCAT Plus was to identify catalyst formulations with better activity and stability than their benchmark catalyst. So we have deployed our experimentally guided Bayesian optimization framework using a software called SD Labs, commercialized by a Swiss American startup called Atinary. And just to give a few words, I mean, that's basically a no-code software allowing chemists without any coding background to implement Bayesian optimization framework easily in their daily lab activity. So as a result, in about 5 weeks of experiment, we produced roughly 100 catalysts with complex formulation for Daphne in a space of several millions of possibilities. And as the loop progressed, you clearly see that the Bayesian model suggests more and more performing catalysts. And some of the top catalyst materials that we have formulated clearly outperform the benchmark catalyst provided by Daphne in terms of stability, which was one of the main criteria of this study. And in a second step, Daphne has scaled up the catalyst synthesis and evaluated the performance of some of the best materials we have identified in their pilot scale unit. So we do observe some deviation between the pilot and the lab scale, but the objective is not to feed our model or to adjust our model with the pilot scale data and to run a second loop of optimization, trying to solve those pilot scale difficulties. I mean, that's just roughly one example, but we have several other projects in different types of catalyst and application.
All right, thank you very much. And definitely Bayesian optimization is one of those names that continuously comes up when you start in this field or when you go forward. It's usually so powerful, Bayesian statistics and optimization. Now the next question is for Brian. And so successful autonomous lab systems, they require universal interfaces and standardized data formats. So the question is, what collaborative models or partnerships between national laboratories, academia, and industry do you think that could realistically drive industry-wide standardization?
I think so. Industrial-wide standardization can be difficult, not just in this field, but across many different domains, because people tend to come up with their own standards, or certain domains will have their own standards and be specific to applications or vendors or what have you. So this is a very big challenge in autonomous science and autonomous laboratories. We need to have the data and metadata and provenance data be able to be managed effectively across the entire pipeline, and be usable by autonomous AI agents to help drive experiments and perform or drive instruments and perform experiments. So it's really crucial to promote maybe not standard data formats, but standard interfaces that can communicate and share data effectively. So this is one of the things that's been popping up recently, and that I want to highlight is that effective communication and collaboration across these sectors, so academia, national labs, government, industry, is insanely valuable in bridging these gaps, because a lot of times these efforts are very much siloed or isolated from each other, and it's hard to get these common interfaces. So there's been some initiatives and community-driven workshops lately that I'll highlight, that have really tried to bring forward-thinking leading researchers across all sectors together to kind of develop and tackle some of these challenges and discuss future opportunities. So with this in mind, there's kind of initiatives at each national lab. So at Oak Ridge, we have the Interconnected Science Ecosystem, which is shortened as Intersect. There's Autonomous Discovery Initiative at Argonne National Lab, at Scale, at PNNL, and several others. But I'll highlight the annual Autonomous Workshop or Workflows Workshop. The first of its kind was last December. The second of this workshop will be this summer, and this is again bringing together researchers from all sectors to collaborate and discuss and really map out the future of autonomous laboratories. And from that workshop came the ISLE Consortium, which is the Autonomous Interconnected Science Lab Ecosystem. So again, community-driven consortium of scientists working together to bridge the gap, not just on creating uniform interfaces, but all challenges with autonomous science. And if people are interested in these efforts, feel free to reach out to me and I can provide more information. But there's a lot of work going on in enabling communication and collaboration across these sectors to promote more engagement in this area.
All right, thank you. And definitely, I think it's especially critical in this field as the number of variables that are inside a design of experiments for catalysis research and development is so huge, then standardization becomes very critical. And now for the next question, we see that the field is rapidly moving from models that actually take little amount of these variables to models that are multimodal, in the sense that they can manage multiple kinds of chemical data. So these systems, they actually have new technical challenges. And the question is for Stefan. With these multimodal models that grab a huge amount of variables, what challenges and opportunities do you foresee, and with what pitfalls should we anticipate?
Yeah, this is a great question. I actually have a very concrete answer to this. This is the kind of early version of these kinds of problems are things that we encountered and had to overcome when building out our recently released AQCAT 25 dataset and associated model that sort of learns on it. The picture that you should have in mind, of course, is that there's applications we want to tackle, and in order to tackle the next application, we have to take everything we've done before, say all the data we've made, the models that we've built, and augment it with some new piece of physics or some new level of increased accuracy and so on in order to extend what we have. And so in the case of AQCAT 25, we turned up we brought in new data, did a lot of new DFT calculations to create this new data set, incorporating some new physics, in this case, spin polarization and the associated magnetic interactions, as well as increased the fidelity by turning the knob on the accuracy of the DFT simulations. But then we had to, we wanted to incorporate that into models that were already pre-trained on data that already existed, because you don't want to just forget everything that you had before. And it turns out that when you naively try and do this, you run into all kinds of problems familiar from the AI world of catastrophic forgetting and so on, where you try to teach a foundation model something new and it forgets what it knew before. And so it's not so straightforward, and you want to maintain this. And so part of the way that we were able to get around this, that you could read about in the paper, is by borrowing techniques from like other completely different domains, like image processing, for example, where you add little pieces, you add a new piece to your foundation model that's there during training that kind of says, okay, now I'm looking at a piece of data that has this level of fidelity and this type of physics, and now I'm not. And it modulates the weights and so on. And I don't want to get into the technical details, but it's there are some very practical challenges that we will have to overcome. But the good news is that those challenges also exist in other areas, so we don't have to reinvent the wheel. And the opportunity is immense, because building out one of the lessons of the last 5 to 10 years in AI applied to anything is that the foundation model approach is very, very fruitful, and we should not discount the potential of what we could do by having these powerful models.
All right, thank you very much. So transfer learning from other fields and other machine learning applications. Yeah. The next question is for Paco. And as the field matures, the attention goes from the creation of algorithms to problems actually related to data quality, integration. How do you put the machine learning into your workflow? How do you orchestrate everything together? So I would like to ask you, what are the main bottlenecks that you are seeing right now that limit the effective deployment of AI-guided catalysis, and how do you see them being addressed?
Okay, so yeah, I mean, I think there are many bottlenecks, but just maybe the two main one, I think I mean, it was probably already mentioned by Stefan and Brian. So I think the lack of massive and standardized experimental databases, and I think it can be related to that is the maturity of lab automation equipment. So on the data side, we mentioned that models could benefit of having access to large quantities of high quality experimental data. And in theory, if you look at what the catalysis community is doing every day, I mean, we in theory would have enough experimental data to feed those models and make them very powerful. But in reality, only a small fraction of the experimental data are digitized and published. And even among the published data, a lot of them are poorly standardized and miss a lot of metadata, leading to reproducibility concerns between labs, between equipment, between operators, and making it difficult for models to be trained and fed with those published experimental data. So we see lab automation as a potential answer to this point, to generate standardized and massive amount of experimental data, because it pushes standardization in protocols, it pushes digitalization. But I think it brings us to the second bottleneck, which is the maturity of lab automation tools. Even if we saw the last years and decades new development of automated platform for heterogeneous catalysis, synthesis robot, high-throughput reactors, automated analytical equipment, softwares like LIMS or even AI type of software. They remain pretty much expensive for most of the research groups, fragile, and they are not perfect. And most of the time, they cover only a portion of the R&D workflow. So as a result, we typically need to combine multiple equipment, multiple pieces of software, which are not so well integrated together. And that leads at the end to break this concept of self-driving labs that you hear a bit everywhere. So yeah, I think to move forward and to help deploy at larger scale those AI guided projects everywhere, maybe the suppliers need to develop new hardwares with features specifically designed for heterogeneous catalyst chemistry, integrate better the different types of softwares together, and we have to enforce more standardized experimental protocols everywhere. So yeah, so that's, I think, the main bottlenecks I see.
All right, thank you. Definitely new designs, as the retrofitting of existing equipment is sometimes so painful. And then for the last question of this section of the panel discussion, it's for Brian. Our experience with machine learning algorithms is that they do what we usually do in hours, they do it in seconds. For example, that's our experience with ChatGPT when writing a report, for example. So I would like to ask you, what do we do to not compromise the scientific oversight of, for example, futures autonomous labs, considering this challenge that they act in so little time spent?
Yeah, this is a great question, and it comes up not just in chemistry and material science, but in all domains looking at, using AI to accelerate their workflows. In fact, I was just at a conference a couple weeks ago, the supercomputing conference in St. Louis, and this came up in almost every workshop, this idea of trustworthiness and reliability of results when you're trying to maximize the amount of experiments you can do and reduce the time it takes to discovery. This inherently pops up, and I'll just maybe tack on with Paco's response that this maybe is another bottleneck that is facing this autonomous science and in this application. But I don't think there's any one size fits all answer to this. I think every domain and every application might have a slightly different solution to kind of mitigating concerns, but there's definitely some important strategies that I think could be beneficial here. So leveraging digital twins. So at Oak Ridge, we do a lot with integrating digital twins to kind of test, validate, and fully flesh out some of these autonomous workflows prior to deploying AI in production resources, and I think that could be beneficial. I think integration of data provenance frameworks is extremely crucial just to track the entire end-to-end process and trace some of the autonomous decisions that are happening. Obviously, integrating some QA, QC mechanisms throughout the process is valuable. But then maybe the final point that I'll make is maintaining human in the loop or human on the loop to some degree, so that there's still the possibility for human oversight and human override capabilities to provide, that kind of resiliency in automated workflows. And I guess one last thing I'll highlight is just continue to educate and develop the workforce to prepare and train for this kind of new future of AI accelerated science, and maybe best train the workflows to use AI effectively without completely replacing maybe their own decision making.
Yeah, thank you very much. Definitely this educational aspect of this future that is already becoming the present. Yes. Before I go to the next question, that is a general question, I left behind a communication that Harsh would be conducting a poll, I believe in the chat. Let me know, Reja or Harsh, if you have to add anything here, if I wait or if I go to the last question, that is a general question.
I think you can go to the general question. The questions are in chat, so while you ask that question, people can still answer the question in the chat.
All right. Thank you.
Yeah.
Thank you. So the last question is more into the prospection, creativity, fantasy space, but of course with also considering your expertise and what you see in the field. The last question is if you can believe that artificial intelligence can lead us to discover a catalyst class that no human would ever propose, or if we're just accelerating traditional chemistry. So I would like to ask this first to Stefan.
I would say, especially looking toward the future, the answer is definitely yes, right? And I would also, I would say even more strongly, even if you think that all we're doing is accelerating traditional chemistry, if that's your characterization of it, the answer would still be yes, because you can accelerate it so much that it's like doing, 100,000 years of traditional chemistry within a human lifetime, for example. And there is so practically speaking, with that much acceleration, no human would ever get around to finding the thing that you found. So yes, even acceleration alone is qualitatively different than what we had before.
All right, thank you. Now the same question to Paco.
So maybe I'm less optimistic, but I think at the moment, at least, let's say from our perspective, we are mostly accelerating known chemistry and material classes. And I think the disruptive power of AI at the moment is more the ability to explore extremely large parameter space and also evaluate millions of potential atomic arrangement much faster than with the conventional tools, but still grounded in the physical and the chemical constraints of the data set with what they have been trained, so the training data set. What I've seen so far, but maybe I'm wrong, is models which are trained for a specific class of material and usually a specific application, and they usually don't predict outside of their training boundaries. But the positive aspect, and I think to connect to what Stefan mentioned, I think AI is already suggesting for catalyst formulations or structures which has not been yet tested by human just because of subjective biases or because of the size of the space. But to discover a new class of material such as MOF or zeolite are considered, I think at the moment it's maybe an over expectation, but the field is going so fast so that maybe it's going to come faster than I think.
All right, thank you. Very balanced answers. One more towards idealism, the other one's realism, and both are important for the community. And let's say Brian's take on the question.
Yeah, I would agree. I think it's definitely possible, and it's probably in our future, but I don't think we're quite there yet. We've talked about it already, but AI is great at search, characterization, optimization, pattern recognition, and it can cover way more space than we can in the time constraints. But I don't see it fully able to use fundamental scientific principles to hypothesize and discover new classes of materials just yet. I don't think that's far away, but I don't think we're quite there yet.
All right, thank you very much. And then I'll let Ria continue the session. Should I go with the slides or first the question and answers?
I can take up the questions. Thank you so much, Jorge. And thank you so much for the panelists for your insightful answers. I have a couple questions in chat that I want to ask. Feel free to raise your hand or unmute and tell me who's going to answer the question. And if you want to piggyback on someone else and expand on that, it's fine too. The first question is, how would you address AI approaches for heterogeneous deactivating catalyst systems that need long-term experimental testing? Who would like to take this question?
I can.
Okay.
I think it's the same issues that you have to evaluate the activation even without AI. I mean, those long experiments are quite difficult. So people are putting in place accelerating aging protocols. And so you could do, I mean, at least what we would do and what we are doing in the lab is we put exactly the same protocols that you would do without AI. And then you define parameters like the slope of the activations or whatever the parameters that you can take out of those accelerated deactivation protocols, and you feed them in the model. But of course, you need to make sure that those parameters and features, they are really meaningful in terms of what you're looking for.
Thank you. We have one more question, which is how AI model can be used to get the active sites in catalysts, especially when active sites of a catalyst coming from the metal support interfacial sites rather than only from active metals. What is your opinion, especially in supported metal nanoparticle catalysts?
So
I would say this would be okay.
Maybe I'll jump in. I don't have a specific answer to this question, but I think I have, a comment that's relevant to both this and the previous question and a whole class of questions. I think it's important to recognize that whenever we're talking about some new phenomenon, some new area of chemistry, some new piece of physics, some new domain that we don't yet have the AI model for, but we want to be able to accelerate. It's important to be grounded in the way we approach. So what you don't do is you just ask the AI model to solve the new problem for you without giving it anything new to go on, right? That's a recipe for getting the wrong answer, right? Mm-hmm. The starting point needs to be some either experimental data, well, ideally both, some experimental data plus some grounded physics model, solve some equations, use some, high performance computing style methods to generate some synthetic data, say, in the area, and then get the AI model to extrapolate from there. But one of the key things that I think is important to emphasize in this whole business is that we can't forget, as excited as we get about AI, we absolutely cannot forget about the other piece. And so there's a whole, even from the computational side, there's a whole other exciting branch of this field, which I count as part of the same field, which is just doing more with like computational physics, computational quantum chemistry, computational this, even without inserting the AI yet, as a fuel for the AI. And so that's my generic general answer for basically all of these types of questions.
Yeah, I think there's a follow-up question on the same lines of what you just answered, which is, are we feeding these models with information of experiments that did not work?
I'll jump in on this one, and
Perfect.
I don't know. I'm sure that information is getting into some of these models, but I would advocate that information should be included with proper annotations and metadata and provenance detailing that is as we make mistakes, even as humans, we learn from those mistakes and get better. So I think it's apply that same kind of logic to AI, in that the more information we give it, whether it's the experiment worked or it didn't work, that is valuable and will help to train and improve it for the next round of experiments. So I think that is valuable.
Yeah, thank you. I want to request Jorge to share the presentation again, please. Or Harsh, whoever has it ready.
Are you seeing it?
Yeah, yeah, that's perfect. Before we wrap up, I'd like to briefly highlight an upcoming TCG study titled AI Advances in Catalyst and Materials Design, Practicalities and Myths. As we all heard today, AI is rapidly reshaping catalyst and materials development, but implementation remains challenging. This study is designed to cut through the hype and focus on what actually works in practice. We're inviting companies to join as charter participants, helping shape the study's focus, while also gaining early insights from leading programs at HDE, BSF, DTU, ORNL, and top institutes. Participants will receive practical guidance on AI, ML-enabled design, global mapping of key players, and clear roadmaps to AI-driven catalysis through 2030. With that, thank you so much to our panelists, Stefan, Paco, and Brian, for sharing your time, your expertise, and your valuable perspectives today. And thank you as well to Jorge for expertly moderating such a thoughtful and engaging discussion. I'd also like to thank everyone in the audience for joining us today and for the excellent questions and for the active engagement throughout the session. A recording of today's session will be sent, and any follow-up materials with the contact information of our panelists and our moderator will be shared with you shortly. If you're interested to learn more about any of our programs or participating in our TCG study on AI, please reach out to us. My contact information is also going to be shared in the email, or feel to visit our website. Thank you again for your time, and we hope to see you guys at an upcoming TCG event. Have a great rest of the day. Thank you.
Thank you, everyone. Nice to meet you.